Alright, so we have a function f from R to R, and its derivative is non-zero at every point on R. And we want to show that it is 1 to 1. Okay, so since f from R to R is differentiable on all of R, f must be continuous. Because if you imagine if f weren't, this might even just be a theorem that we have from previously, and so we don't need to go back and prove it, but I don't know, you get to a point where there's just so many theorems floating around in math that if you can, like, convince you or prove something to yourself really quickly, then that's typically faster than going back and looking it up and seeing if this is actually something that you've proven. But yeah, so if you imagine if f is not discontinuous, it needs to either have, and this is of course a real valued function, a function from R to R. So if it's not continuous, then it's either got to have a jump discontinuity or like some sort of asymptotic or oscillatory discontinuity. And if you have, even if it's oscillating, yeah, so basically the second kind can't really happen because f is differentiable. Or not even so much that. Like if you have like an asymptote at a certain point, then the function isn't defined at that point. Unless you have something like you have a left limit which exists and a right limit which doesn't exist or something like that. But the point is, if you look at the definition of the derivative, if you look at that limit, then the numerator in that limit needs to go to 0. And so that rules out any sort of discontinuity. And so for f to be differentiable on R to R, f needs to be continuous. This wouldn't necessarily be true if f were differentiable on, like, the real line minus a single point, but the fact that it's differentiable on all of R means that f is continuous on all of R. So now we can apply the mean value theorem and say if you have two real numbers, a which is less than b, and f of a equals f of b, then there exists some c which is strictly between a and b, such that if we take f prime and evaluate it at c, then this is precisely f of b minus f of a over b minus a. But in this case, the existence of such a c is guaranteed by the mean value theorem, but now we know in particular that f of a equals f of b. And so then the numerator is just 0, and so this is 0. So this would contradict the fact that f prime is equal to 0. F prime is not equal to 0 everywhere. So it cannot be the case. So what this means is that if a and b are distinct points, then f of a cannot be equal to f of b. And that is precisely what it means to say that f is 1 to 1. And this holds for all a and b and R, and so f is in fact 1 to 1 on all of R. Let's see here. So this relies on mean value theorem. I forget if we've proven mean value theorem in this textbook, but again, in fact, I think mean value theorem, you prove it by first proving Rolle's theorem, which proves it. Well, actually, this might be an application of Rolle's theorem rather than the mean value theorem itself. But in any case, I think it's something that you have to take the time to prove. So it might just be one of these things that we borrow from calculus and say, hey, we haven't proven this, but it's true, so let's use it here. Because I don't think they'd expect you to actually prove Rolle's theorem in this exercise. Because it gets its own section in its own theorem in, say, Principles of Mathematical Analysis, i.e. Baby Rudin. Okay, so that's part A. Now let's move on to B. So basically what we're proving is that this doesn't hold in Rn. Or, well, we're not proving that doesn't hold in Rn, we're proving that doesn't hold in R2. Although I guess you could easily extend this to Rn. By just taking, if you have n greater than 2, then you just define f in the first two coordinates to be defined like this, and then for the remainder of the coordinates in the domain you don't include those variables, and then the codomain you just set all of them equal to some value. But anyways, what's important is that this fact doesn't hold in higher dimensions, and this is like a big thing if you're studying like functions of higher dimensions, like what facts about functions of lower dimensions extend, and this is not one of them. So let f be defined here. F of xy is given by this function. So if we want to compute the determinant of f prime of xy, so f prime of xy is a matrix, and so here when I write the absolute value of this matrix, I'm using like the absolute value notation, but it really means determinant, like you'd see typically in linear algebra courses. If you want to take the determinant of a matrix, you just use vertical lines on either side of the matrix. So that's what I mean by vertical lines here. This is not the absolute value of f prime of xy. So anyways, this is equal to, and now we can really see how we're using the absolute value to mean determinant. Okay, so first row we use the first function and take its derivative with respect to the different variables, and then the second one. So this is just your standard Jacobian matrix. Dx sine y. Okay, so now we actually take these derivatives. Well, taking the derivative of e to the x doesn't change anything, and then the other thing relies only on y, and so it's a constant. Then as for the other thing, derivative of cosine of y is going to be negative sine of y. So this is going to be minus e to the x sine of y. And then here we're going to get e to the x cosine of y. Alright, and now we can actually take the derivative, determinant. And so we have e to the x times e to the x. And e to the x times e to the x is going to be e to the 2x, because that's how you add exponentials. And then cosine of y times cosine of y is going to be cosine squared of y. Now we subtract the product of the other two entries, and there's a minus sign here, so we're actually going to end up adding. And again we have e to the 2x, and then we're going to get sine squared of y. But then we can factor out e to the 2x, and so then we have e to the 2x times sine squared plus cosine squared. And of course, sine squared plus cosine squared is always equal to 1. And so this is just e to the 2x times 1. And we know that the exponential function as a function from r to r is never 0. It only takes on strictly positive numbers. So this is not equal to 0. So let's here define f. So what we want to do in this problem is define f as such, show that the determinant of f prime is not equal to 0 for all x and y. So that's what we've just proven. We've computed the determinant of f prime of xy and shown that's non-zero. However, we want to prove that f is not 1 to 1, and this should be sort of straightforward since sine and cosine are periodic functions. However, sine and cosine are 2 pi periodic. So if you take f of xy, this is going to be, so the e to the x cosine y, e to the x sine y. So if you replace y with y plus 2 pi n for any integer n, then you're just going around the unit circle some number of times and ending up back where you started, and so the value is not going to change. So f of x y is going to be equal to f of x y plus 2 pi n for any integer z, and thus f is not 1-to-1, because there are many, in fact there are infinitely many, like if you have f of x comma y, then there are infinitely many other pairs of numbers that you could input into f to get the same output, which is not, it's not allowed for 1-to-1 functions. And so, yeah. So the derivative of a function being non-zero, implying that f is 1-to-1, is a true statement of functions from R to R, but it's not true of functions from R2 to R2. And you could extend this if you wanted to prove that this is not true of functions from Rn to Rn. And yeah, that's the whole point of this exercise, so we're done.